For billions of years, our planet has traveled in a stable orbit around the Sun. At an average distance of nearly 150 million kilometers, Earth exists in a narrow region of space where conditions are neither too hot nor too cold. This distance is known as 1 astronomical unit. It may seem like just a number, but it is the invisible boundary between survival and destruction. Within this narrow band lies what scientists call the habitable zone, the region where liquid water can exist on a planet's surface. And without liquid water, life as we know it would not be possible. Earth's position is not accidental. It is the result of gravity, motion, and billions of years of cosmic balance. But what if that balance shifted? What if Earth moves just 1% closer to the Sun?
Water vapor from evaporating oceans
rises into the atmosphere. At first, 1% sounds insignificant, a tiny adjustment, almost harmless. Yet 1% of 150 million kilometers equals roughly 1.5 million kilometers. That is nearly 4 times the distance between Earth and the Moon. In cosmic terms, this is not small. It is enormous. The amount of solar energy reaching Earth depends on distance, and this relationship follows a principle known as the inverse square law. When a planet moves closer to its star, even slightly, the intensity of radiation increases more than we might expect. A 1% decrease in distance would result in roughly a 2% increase in solar energy hitting Earth. 2% may not sound dramatic, but Earth's climate system is incredibly sensitive. Global temperatures could rise by several degrees Celsius over time, and even a small rise in average temperature can destabilize entire ecosystems. Polar ice caps would begin to melt more rapidly. Glaciers that supply fresh water to millions of people would shrink. Sea levels would gradually rise, threatening coastal cities across the world. Storm systems would gain more energy from warmer oceans. Hurricanes could become stronger. Heat waves would last longer. Droughts would intensify. Agricultural regions near the equator would struggle to produce crops. Water scarcity would increase. Food prices would rise. Migration pressures could grow. Entire economies would feel the strain. But warming alone is not the greatest threat. The real danger lies in feedback loops. As temperatures rise, ice melts. As ice melts, less sunlight is reflected back into space. Instead, darker ocean water absorbs more heat. This leads to further warming, which causes even more melting. This cycle can accelerate over time. Another feedback mechanism involves water vapor. As the planet warms, more water evaporates into the atmosphere. Water vapor is a powerful greenhouse gas. It traps heat. More heat leads to more evaporation. More evaporation traps more heat. If this process continues unchecked, Earth could approach what scientists call a runaway greenhouse effect. This is what likely happened on Venus. Venus may have once had oceans, but because it orbits closer to the Sun, increased heating caused massive evaporation. Water vapor trapped heat. Temperatures rose further. Eventually, the oceans disappeared entirely. Today, Venus has surface temperatures exceeding 460 degrees Celsius, hot enough to melt lead. Could Earth follow that path? With only a 1% shift, a full Venus-like transformation is unlikely in the short term, but over centuries or millennia, the risks would increase. The balance that keeps Earth stable would weaken. Life would adapt where it could, but not all species would survive. Tropical ecosystems could collapse under extreme heat. Coral reefs would bleach and die. Arctic habitats would vanish. Animal migration patterns would change. Biodiversity would decline. Human civilization would face unprecedented challenges. Infrastructure in hot regions would need redesigning. Energy demand for cooling would surge. Urban planning would shift toward climate resilience. New technologies might be developed to manage solar radiation, perhaps massive reflective structures in space, or atmospheric interventions designed to cool the planet. But such geoengineering solutions carry their own risks, and they would require global cooperation on a scale humanity has rarely achieved. Meanwhile, Earth's orbit itself would remain gravitationally bound to the Sun. A 1% shift would not send the planet spiraling inward, but interactions with massive planets like Jupiter could influence long-term stability. Over millions of years, gravitational resonances can amplify small orbital changes. Space is dynamic. Nothing is perfectly fixed. The remarkable truth is that Earth already exists near the inner edge of the habitable zone. Move slightly closer, and oceans begin to warm dramatically. Move slightly farther, and global freezing becomes a threat. The margin is thin. Compared to thousands of exoplanets discovered in distant star systems, Earth occupies a rare position, a narrow window where chemistry, physics, and time align to allow life to flourish. And sometimes, survival in the universe depends on precision, on distance measured in millions of kilometers, on temperature differences of just a few degrees, on shifts as small as 1%. From our perspective, 1% seems trivial, but in space, 1% can reshape a planet. It can transform climates, redraw coastlines, alter ecosystems, challenge civilizations, or over long periods of time, change the destiny of a world. Earth's stability is not guaranteed forever, but for now, we remain in balance, orbiting at just the right distance, receiving just the right amount of energy, living within a narrow band of cosmic safety. And perhaps the most extraordinary realization is this: our entire existence, every ocean, every forest, every city, depends on a fragile alignment in space, a balance so precise that even a shift of 1% could change everything.